Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're getting a little controversial. The other day, shortly after the Florida Panthers beat the Edmonton Oilers in Game 7 to win the Stanley Cup Championship, a rabbi had asked me if there were any particular reasons why the team that had the 3-0 lead and would then lose it would be more likely to win, because those teams had won 11 of those 16 matchups combined between the MLB, NHL, and NBA playoffs. And I told him that it very well may be that it really is 50-50 and that this 5-11 split was just randomness, but that it would take some rather complicated math analysis. I also gave him the hint that the conventional analysis that they teach first-year stat students is wrong. And it's not really that mathematicians are holding out on the first-year stat students. The experts are wrong on this one. Well, a lot of the experts are wrong on this one. And that instead, the conventional approaches in a lot of areas are fundamentally flawed and wrong. Now, I should probably be careful about saying that, unless I want to start a math war. And you know what? I want to start a war! Whoa. We're mathematicians here. We don't fight with knives. We fight with chalk. Ah, okay. So, based on this situation that arises from sports, let's start with the problem statement. Combined between the MLB, NHL, and NBA, 16 teams have fallen behind in a 3-0 in the playoff series, then tied the series 3-3, and of those 16, 5 have won Game 7, which then won the series, while the other 11 lost the game and lost the series. And the question is, well, got a couple of different questions we could ask. First of all, what's our best estimate that if this were to happen the 17th time, what's our best estimate of the probability that the team that fell behind and tied it would then win versus falling behind, tying, and then losing after coming oh so close? And in addition to just getting our single best estimate, we might want a range of what the reasonable estimates are, right? So a range of reasonable values for the true probability. And then there's also just, all right, if two teams are facing each other and you know nothing about the two teams, and there's a 50-50 chance that you'll pick the winner, given no information. So you could just say, well, this 5 out of 16, is that enough to convince us that the true likelihood actually differs from 50%? Or might the true likelihood really be 50% and this was just randomness? So those are three slightly different questions. And in this video, I won't be presenting here anything that actually does it right. This is part 1 in a video series. This first part is just explaining why the conventional approach they teach you in an intro to stats class doesn't work. And why it really can't be modified easily to work, and why I'll even go so far as to say that you'd be nuts to think that something like that would work. And I realize saying all that is kind of, yeah! But I'm saying it anyway. Before I get into all the details, let's simplify the problem, or let's simplify the situation. Let's suppose instead of 16 and it's being 5 one way, 11 the other way, suppose that we had 5 observations rather than 16, and that all 5 went one way. So looking at 3 different situations, suppose I pull out a coin from my wallet and start flipping it, and I get heads all 5 times. That's one situation. Another situation, suppose I'm working in a supermarket, and I go into storage and I reach into an unmarked crate of fruit from a distributor that only sends apples and oranges. I grab 5 fruits from the box, and they're all apples. In some ways, those are similar, right? 5 trials, 5 successes, if you want to define it that way. But you feel like there are some differences as well. And then, going more in the sports direction, suppose I'm checking the standings of just nearby sports league. I know nothing about the teams. I just look, oh, the local team is 5-0. has won 5 games in 5 attempts. So those are 3 analogous situations in the sense of 5 events, 5 successes. So mathematically, it would appear that they're all the same. Now, if we were to ask, over the next 100 trials, what would we expect? In these 3 different scenarios, which look the same mathematically, we should expect 3 different results. For coin flipping, it's probably a fair coin. You'd predict another 50 heads and 50 tails. In the fruit case, hey, who are you calling a fruit case? You know that's not what I meant. In the case dealing with fruit, we should predict that we're pretty sure this is a box full of apples. The only thing preventing us from pulling another 100 apples out of the box is that maybe there aren't 100 apples in the box left to begin with. But we'd be surprised if there were anything other than apples in there. And in the sports case, it's a little harder to come up with an exact prediction. But you'd expect, when a team starts 5-0, you'd be somewhat disappointed if the team were to win 50 of its next 100 games. You'd be really amazed if they won all hundreds, so the number that you expect them to win is probably a bit more than 50, noticeably less than 100. It's really going to depend on the specifics of the league. And some of that we can't quite get into here. Some of that we'll get into starting in part 2 of the video. But one thing to point out here is that realistically, you have 3 very different conclusions. If you were to say, what do we expect to happen the next 100 times? You're getting very different answers to those questions. Any sensible mathematical approach should give you different answers to those questions. And if you look at the approach that they teach you to use in an intro to stats class, it doesn't give you different approaches to those, different answers to those questions. Therefore, the approach that they teach you in an intro to stats class is insensible. All right, so any mathematical approach has to actually rely on some sort of numbers in math or something like that. So how would we mathematically express the difference between those, or the differences between those 3 different cases? The setup appears the same. We know that there are similarities. 5 trials, 5 successes. The difference relies in what we call the prior distribution. The question, what did we expect, or what would have been reasonable to assume about the success probability or success rate before we even saw any of the data? So with the coins, right, most coins have 50% chance of coming up heads versus tails. So if you plot that out over the success rate here, most of that weight is over here, right, centered at 50%. And so you'd need really convincing evidence to move it away. And maybe there are slight deviations, and there are the occasional weighted coin, so maybe this graph is somewhat of an exaggeration. But note the difference between that and the fruit case. Hey, you know what I meant. The supermarket case, where there's a decent chance that all the fruit are oranges to make a 0% apple rate, or decent chance that they're all apples, not much in between. And then for the sports team, we know that there are some average teams, there are some slightly better than average teams, there are some slightly worse than average teams. The distribution kind of probably follows around a bell curve, sort of like this. How spread out that bell curve would be would depend on the specifics of the league. We'll look more into how that applies to those 3 major leagues of sports in part 2 of the video series. But somehow you'd have to rely on this prior distribution to actually come up with any sort of sensible approach. So now that we've established that you need to look at this prior distribution, and we know that conventionally they don't, all right, this leaves the question, what heresy does the infidel teach? Dr. Nighttime, we know this isn't being published in a full scientific journal. But do try to keep this a little bit professional and avoid words like heresy and infidel. Fine. How's this? What's the conventional approach? Okay with my phrasing it that way? Yeah, that way's fine. Alright, so we ask, what is the conventional approach? Well, we'll start with the conventional approach to the question, are we reasonably convinced that the true likelihood differs from 50%? Right, we've seen 5 out of 16 in this case. Are we convinced that's too low? Now, ideally, we look at our observations, right, 5 out of 16, and we want to say, all right, if it's closer to 50%, then we're convinced that it's 50%, and if it's really far from 50%, then we'd say, yeah, we're pretty sure it's not 50%, and then there's going to be some sort of threshold. With something else in there as well, we have to worry about whether or not our test is conclusive or whether we just have insufficient data, right? If it happened if we observed 2 of these situations, and in one case the team that took the 3-0 lead won, and in the other case the comeback team won. So in that case, since we're dealing with a sample size of 2, that's not enough to conclude that the true probability is probably specifically 50%. This conventional approach doesn't really have room for distinguishing between too high, too low, just right, and insufficient data. So that's already a flaw with this. But then the question becomes, if you're looking at further deviations, right? If you're seeing further deviations from 50% and you're concluding, okay, that probably means the true average isn't 50%, well, it leads to the question, how far away from 50% is too far away? As we have to decide where to set our threshold. If we set it too tight, right? If small deviations away from 50% would mean that we conclude, no, that the true number really isn't 50%, we risk getting fooled into thinking that just by random chance, you might think, okay, there really is something systematic and repeatable going on. Whereas if it takes us too much convincing, right, if you've got too wide a range in which you say, that's close enough to 50%, well, then you risk getting fooled the other way. That first mistake is called type 1 error. Second mistake is called type 2 error. And ideally, you would need some way of balancing the risks of type 1, type 2 errors. So the sensible thing to do would be to try to balance those. However, this insensible approach instead says, don't balance at all. Instead, just have a wide enough range that there's only a 5% chance of a type 1 error. And once you're doing that, you want the most powerful test you can. A test is considered powerful if it avoids a type 2 error, because that's type 2 error, again, is when you're saying, all right, we've got this boring case of saying, oh, everything's 50%. And if you can successfully determine or identify the cases where the underlying percentage isn't 50%, then you've got a stronger test. So you're trying to get the most powerful test that you can get that won't make a type 1 error more than 5% of the time. It's an arbitrary threshold. You're not actually balancing the risks. It's malarkey. Can I say malarkey? Yeah, saying the word malarkey is fine. All right. So it's malarkey, and unfortunately, it's malarkey that's become the industry standard in a number of things. Which, I know saying that is kind of... but that's part of the point of this video. Alright, so let's see this tomfoolery in action. Tomfoolery okay to say? Yeah, go ahead. Tomfoolery is a fine word. So, what the conventional approach would say to do here, if you were to assume for the moment that the true probability of the comeback team going on to win the series were 50%, then out of 16 attempts, you could keep track of the probability of the comeback team winning anywhere from 0 to 16 of those series. And with a computer algebra system, or lots of pen and lots of paper if you're into that kind of stuff, you can come up with the probabilities. What we would say is, all right, suppose for the moment that our threshold was was close enough in that getting 5 out of 11 successes, or sorry, 5 out of 16 successes, suppose that would be enough where we'd say, no, the true probability is probably not 50%. suppose we said that, and we set our threshold. Well, then if we add up all these probabilities up here, where you have 5 successes or fewer than that, or on the flip side, 11 successes or more. When we add all those up, we get what's called a p-value of 21%. This means that if we were to set up a test, if we were to define a test saying, once you're at 5 or more, or at 5 and 11, or 11 and 5 out of 16, or anything more extreme than that, if you were to do that, then if the true probability were 50%, you'd have a 21% chance of making a type 1 error, which, according to our arbitrary, foolish poppycock rules, poppycock, okay? Yeah, the word poppycock is an accurate enough description. So according to those poppycock rules, what we'd be saying, all right, 21% chance is too high. And so you need to see a greater deviation to conclude that the probability of success was not 50%. And looking at this, it means you need to either see 3 and 13, or 13 and 3, or something more extreme than that. That's what you would need. All right, so we do all this. We say out of 16 observations, if anywhere between 4 and 12 are there, we can't conclude that the true underlying probability is different from 50%. That's what this hogwash approach? Hogwash approach. That's what this hogwash approach says. And let's see some of the other issues with this. The first big thing to notice is that it does absolutely nothing to account for the prior distribution. And as I mentioned before, it does nothing to distinguish between probably 50% and insufficient data. A bigger issue that they don't really like talking about in these intro to stats classes, because that's where this method starts to fall apart and they're too embarrassed to talk about it. Suppose that we saw that 3 out of 13 times the comeback team won. Alright, so if we're convinced that it's not 50-50, it's got to be somewhere lower than 50-50, but do we automatically say it's 3 out of 16? That seems a little extreme. It's probably somewhere in between those two, but where in between? This approach doesn't have a good answer for that. Note that if you try to say, oh, it's just 3 out of 16, that would mean that if you just barely tick over the threshold, a single event would drastically change your estimate for the probability, which should not happen. This 5% threshold is kind of arbitrary, and one of the fixes that some people try to apply is saying, oh, well, just use different thresholds for different situations. Yeah, what's your rule for which threshold to use when? You're going to have to come up with something else arbitrary and have an arbitrary set of rules for which one to use when. And also, if the whole point of this test was to try to answer the question, are we reasonably convinced that the true probability is 50% or is different from 50%, it makes sense to ask the question, well, what's the probability that the true success rate is 50%? And this does not do that. The closest this p-value that was presented says, if the true rate were 50%, under that condition, what would be the likelihood of observing the sort of thing that we observe? But that's kind of the opposite of what we want to do. We want to answer, given that we've observed what we've observed, what does that do to the probability that the true proportion is 50%? So you're kind of flipping what's observed and that we assume it has to be true because we observed it, versus our if-then, right? If this is true, then what's the likelihood that something will happen? We've observed 5 comeback wins out of 16 attempts. We're trying to guess the probability that the success rate is 50%, as opposed to what the method tells you to do, which is assume for the moment that the success rate is 50%, and guess, and ask, what's the probability of observing 5 out of 16 attempts, or 5 comeback wins in 16 attempts? Now, there is a formula to relate these. It's this formula down here, Bayes' theorem. It says that to relate the probability of some explanation given an observation to probability of that observation happening if that explanation were true, well, you have to take the flipped probability, right? Probability of getting the observation assuming your explanation was true, multiply that by probability that your explanation was true, and divide by all the different ways that you can see that observation happened in the first place. And these two probabilities here, we don't have those. And without some approaches, either using the prior distribution or at an absolute minimum, using some parameters and statistics about the prior distribution. Without that, you can never get the probability that you're looking for. And that's a real problem with this conventional approach that, for some reason, is heavily in use and should not be. All right, now, that's everything that goes wrong when you're trying to estimate the true underlying value and getting your best estimate for that. Now, if you remember, one of the other questions was saying, let's get a reasonable range for what the true underlying value could be. Because there's another approach that they'll teach you in an intro to stats class that is a little more well-founded, but still makes an assumption that isn't necessarily right, and certainly isn't right in the context of sports. This is the method of confidence interval. So, with some caveats here. The conventional method that they teach in intro to stats class for confidence intervals also completely ignores the prior distribution, so there's no way it's going to be right, but I better talk about it anyway, because the folks teaching intro to stats are talking about it. And so if I just try to ignore what they're talking about, then they can say, but you didn't talk about this, so I'm talking about it now, and how horrible it is. Now, even in the intro to stats class, they do warn that this approach is only an approximation for the confidence interval, and that the approximation is only reasonably accurate if you've observed at least 10 successes and at least 10 failures, which in this case, we've observed 5 and 11, and we can't really do anything else about that. And there is a way to try to fix it that we'll get into in part 2 in the video, but that they don't get into in intro to stats. And if they were to get into that, it would kind of naturally lead to the big fix for all of this. That would completely scrap most of the conventional approaches. And what's worth noting here is that, so for this case, if you just look at the parameters we have this p-hat observed success rate of 5 out of 16, corresponding standard deviation of 0.116. Don't worry too much about how to calculate that. I'll get into that and why we use this, because standard deviation itself is a really weird thing to try to calculate that there are reasons to use, but almost nobody talks about why. We'll address that in part 2. Yeah, lots of stuff happening in part 2. But anyway, with all that, the 95% confidence interval would say, well, we think that the true underlying success probability is somewhere between 9% and 54%. I think that tells us a whole lot. And if you wanted the 99.9% confidence interval, just to show you some of the silliness that happens here, if you just plug that approach in, you get that it's somewhere between -5% and 67%. Obviously, that's so nonsense, even the intro to stats professors know that it's nonsense, right? You're getting a negative probability in there. And that's part of why they give you the caveat, only use this if you've observed at least 10 successes and at least 10 failures. And that 10 and 10 rule is specifically to prevent these negative probabilities from showing up. So that much they actually fix. Hey, the experts actually fixed a problem once. But for next time, we'll talk about how to fix all of these issues. I'll talk about how to develop a good prior and then the method for using it. The correct approach to building a confidence interval that still works even if you don't have at least 10 successes and at least 10 failures. a way of modifying this confidence interval, if you really, really, really want to pretend that you can ignore priors, just it serves as a decent fix for that one case of, okay, if you want to mostly do stuff the way that they teach in Intro to Stats, and the one problem you have is that your sample size isn't big enough and that you have at least 10 successes and at least 10 failures, here's how you can actually build a confidence interval with the underlying assumptions they're making and a hidden assumption. There's a hidden assumption about what the prior would be that they just kind of use, but don't like to admit that they're using because they don't want to say that they're assuming anything. They want to say it just works. And I'll get into all of that in part 2. There's more work that needs to go into making part 2, but for now, this is Dr. Nighttime wishing you a good night.